In this video, we're going to continue looking at the idea of critical points and optimization of functions of two variables, looking at some more complex functions and examples. So first, we're going to look at a contour diagram and use that to estimate the mins and maxes, both the local and global mins and maxes of this function. So to look at the global max or any kind of max, we're going to try to find the largest contour that we can see. And the largest one that is labeled is this 7 here. But just because that's the largest one that is labeled does not mean that that is the largest contour itself. In fact, the largest contour is going to be the one kind of inside of that, this contour right here, which is going to correspond to the value of 9 because each one is going up 1. We have, here's 2, 3, 4, 5, 6, 7, 8, and that means that's a 9. And that is the biggest contour we have. That's going to correspond to the global max. So the global max is the value of 9, and it happens at the point, looks like, whatever this x value is, whatever that y value is, right? Each section is going to correspond to 1. So this is in between the 5 and the 6. This is in between the 4 and the 5. We're going to estimate this, and let's just say this is about maybe x is 5.2 and y is maybe 4.8. All right. Let's do the global min. That is the smallest value. The smallest contour we have is this -2 here. It might be kind of hard to see the negative there, but a -2. But similarly, that doesn't mean that's the smallest contour. It's just the smallest one labeled. The smallest one is actually the one inside of that, corresponding to a -3. So again, looking at the x and the y values there, we have a global min, which is equal to -3. That's the global min itself, and that happens at the value x equals 1, and y looks like maybe 3.8 or so. What we're really going to focus on more than anything is the point that it happens at, rather than the actual value itself. But it's important to know that the max and the min itself are the function values, but they happen at the xy points. Lastly, there's one other min or max here, and that is this value of 5 here. That is the top of a little mountain. Everything goes down if you kind of go down that point, but it's not the biggest value. So let's make this green here. That is going to be a local max, and that's going to be equal to 5. It's going to happen at about 1.5 or so, maybe 1.6, a little bit bigger than 1.5. And again, the difference between a global max and local max just has to do with it being the biggest near it or the biggest all around. The 5 represents the top of some mountain. That's important. It's good to know that it's there, but it's not the biggest mountain, and that gives us some more information. All right. Next example, let's find all critical points of the function x cubed plus y squared minus 3x squared plus 10y plus 6. And then we're going to classify each as a local min, local max, saddle point, or none of these. So here is just kind of a standard example with a more complicated function of find the critical points, classify them with the second derivative test. So first step to find the critical points is we need to find the derivative. But for functions of two variables, the derivative has two different meanings. It could be the partial with respect to x or the partial with respect to y. And we are going to find both of these to find the critical points. So first, let's find the partial with respect to x. That is the derivative of this function where we set y equal to a constant. So this y squared is a constant, this 10y is a constant, and the 6 is a constant, and everything else is just in terms of x. The derivative will be the derivative of x cubed, which is 3x squared, the derivative of a constant, which is 0, the derivative of negative 3x squared, which is minus 6x, and then everything else is 0. And then if we look at the partial with respect to y, everything with x is constant. So the 6 is also constant, but the x cubed and minus 3x squared are constant. And the other derivatives are just kind of normal derivatives there. We have the derivative of y squared is 2y, and the derivative of 10y is 10. So now we are going to set both of these functions equal to 0 and find all points that satisfy both equations. So let's start with the 3x squared minus 6x equal to 0. If we want to solve that equation, we can use the quadratic formula, but more importantly, we can factor that left-hand side. There's a 3 in common in both terms, and there's an x in common in both terms. So if we take that out, we'll be left with an x in the first term and a 2 in the second term, minus 2. And if we set that equal to 0, we get x values of 0 and 2. We do the same thing for the other derivative, 2y plus 10. That one's a little bit easier to do. We can just kind of solve for y there. 2y equals negative 10, subtracting 10 on both sides. Divide by 2, and we get y equals negative 5. So those are not our critical points. Those are just the values to kind of get us our critical points. We know that in order to satisfy both equations, x can be either 0 or 2, and y has to be negative 5. So I'm going to kind of put that in words just to say what that means. Right? This is not a necessary step, but just to kind of understand this. This is saying that to satisfy both equations, which is what we need, x is either 0 or 2, and y has to be negative 5. So that means that we have 2 critical points that come out of that. Again, we know that y has to be negative 5, but there's 2 options for x. We could have x be 0 or x be 2. So we have 2 critical points here, 0, negative 5, and 2, negative 5. And that is half the battle, finding the critical points. The other half of the battle is identifying or classifying those as mins, maxes, saddle points, or none of these. That is going to use the second derivative test. So the second derivative test to review is going to use this special value d, which is looking at fxx, fyy minus fxy squared. And we're going to look at if that value is positive or negative. So that means that we need to find all 3 of those second order partial derivatives. So let's do that. fxx is the derivative of the 3x squared minus 6x with respect to x. That's going to give us a 6x minus 6. The fyy is the partial with respect to y of the partial with respect to y, the 2y plus 10. That'll give us just a value of 2. And the partial fxy is the partial with respect to x of 2y plus 10. In that case, that's going to be just 0. And note that that's the exact same thing as fyx, and that's why we get that fxy squared. So this value of d here is going to be 6x minus 6, that's fxx, times 2 minus 0 squared. We could write that if you want. Actually, let's just leave it like that. It's just going to be 2 times 6x minus 6. Or 12x minus 12, or you could factor out the 6. 12 times x minus 1. All right, so now we need to think about the 2 points. So the first point is the point 0, negative 5. So we are going to plug in that point into d, 12x minus 1. So that's going to be like d of 0, negative 5 is going to be 12 times x minus 0. Sorry, not x minus 0. 0 minus 1. We plug in 0 for x. And that'll give us a negative 12. That is less than 0. So the second derivative test tells us that that's going to be a saddle point. And we are done with that point. The other point, 2, negative 5, we plug that into that value of d, and we get a value of positive 12, which is greater than 0. So that's going to be a min or a max. We have to plug it into the fxx to determine which one it's going to be. So fxx of 2, negative 5, we've kind of already done this work. That's going to be 6 times 2 minus 6. I don't really care what the value is. I just know that this is positive. So that's going to tell us that we have a local minimum. There's something about this function being concave up in the x direction, which means we're going to have the bottom of a valley. So our answer here is we have a critical point at 0, negative 5, and that's going to give us a saddle point. We also have a critical point at 2, negative 5, which will give us a local minimum. Let's look at some visualizations of this function to kind of see where those 2 points will come from. So here's our function, and we have a contour diagram on the right, and then the actual function itself in 3D, where the contours are given on the function. We have a local min at 2, negative 5, kind of right in the middle of that contour, and that's going to correspond to the lowest point right there in the actual function. It's that point right there. That's going to be the bottom of some valley. It is not the global min, as this function curves downward a whole lot as we go that direction, but it is a local min. It is the bottom of some valley. And then there's some kind of special point here at 0, negative 5, that being a saddle point. And again, the idea is that this is going to be the top of something. If we go, that's a bad thing to draw. That's going to be kind of the top of some parabola there in the x direction, but it is the bottom of the valley in the y direction. The contours go down in the x direction in both directions, and they go up in the y direction. So there's our two critical points there, local min and a saddle point, though neither correspond to a global min or global max. One more example here, a application problem. Here we have a missile has a guidance device which is sensitive to both temperature in degrees Celsius and humidity. The range in kilometers over which the missile can be controlled is given by range equal to 28,900 minus 5t squared minus 6ht minus 3h squared plus 380t plus 240h. And the question is, what are the optimal atmospheric conditions, that is degrees Celsius and humidity, for controlling the missile? Right, so we have some kind of formula here that tells us with different temperatures and different humidities what is going to be the max amount of range that we can control the missile. And we are trying to find the optimal conditions. We're going to try to optimize this function. That is, we're going to try to maximize the range. We're trying to maximize that function, which means that we're going to try to find the global max of that function. So to do this, we need to find the critical points. We're going to have to try to classify the critical points as mins or maxes and try to find the max, and then in some way try to say that that is the global max. So for some notation, instead of calling this the range, I'm going to call this just capital R. That's our function. So we need to find our derivatives. So let's look at the partial derivative of R with respect to t. And then we'll also look at the partial derivative of R with respect to h. And we'll set both of those equal to 0. So when we're thinking about with respect to t, let's look at all the constants we have there. 3h squared will be constant, 240h will be constant, 28,900 is constant, and then also this 6h is constant, not the t part, just the 6h. So that derivative will be the derivative of minus 5t squared, which is minus 10t. The derivative of negative 6ht with respect to t is just going to be minus 6h. It's the constant times t. And then the derivative of 380t is 380. Do the same thing for h. Here the constants are the 28,900, the minus 5t squared. Here the minus 6 times t, and the 380t are all constants. The derivative will be minus 6t. That's minus 6h, minus 60 times h, minus 6h. That's from the minus 3h squared, and then plus 240. All right, so we have our partial derivatives. We need to set both of these equal to 0, and then find the ht points, or the th points, that satisfy both of these equations. So what we're going to do is we're going to set up a system of equations here. We have two equations and two unknowns. We're going to set up a system of equations. So this first one, if we add the 10t and the 6h over to both sides, we can write this as 10t plus 6h is equal to 380. And if we do the same thing on the other one, let's add 6t and 6h to both sides. We're going to kind of flip it around as well. We get a 6t plus 6h equals 240. So two equations and two unknowns. How do you solve this? Well, there's two different ways you can go about it. you can either do a substitution method or an elimination method. This is from an Algebra 1 or Algebra 2 course. The solve for one variable or get rid of one variable. We'll use a substitution method here. So I'm going to look at this 6t plus 6h equals 240. And let's write this as 6h is going to be 240 minus 6t. And what I'm going to do is I'm going to plug in that 6h into the equation above. 6h is 240 minus 6t, so I'm going to write this as 10t plus 240 minus 6t is equal to 380. Combining all like terms, I have 10t minus 6t is 4t. And if I subtract the 240 on the other side, that'll give me a 140 on the other side. So then I'm going to divide by 4, and that'll give me a value of t equal to 35. Then I can use that point, or that t equals 35, to plug that into either one of the other equations to find the value of h. So I'm going to plug this into the 6t plus 6h equals 240, which will give me 210 plus 6h equals 240. Subtract the 210 over, we get 6h equals 30, so h is going to be equal to 5. So we have one critical point in this function, one point that satisfies both of those equations, and that is going to be the point t equals 35, h equals 5. And now we need to classify that critical point as hopefully a maximum. So we can say that that is going to be the maximum there. So again, we have d is equal to fxx fyy minus fxy squared. We need to find all those derivatives. So fxx, oh sorry, not fxx. Here we're going to do ft is going to be negative 10. FHH is going to be a negative 6. And FTH, which is equal to FHT, is going to be equal to the derivative of either one of those with respect to the other variable. So let's look at the negative 10t minus 6h plus 380. The derivative of that with respect to h is minus 6, and that'll be the same in the other direction. So here our d is not a formula, but it's just going to be a constant. It's going to be negative 10 times negative 6 minus negative 6 squared. That's going to be a positive 60 minus 36, and that's going to be bigger than 0. And that tells us that we have either a min or a max. And since FTT was less than 0, this tells us that we have a maximum. That's all we're going to need here to say that we have a maximum at T equals 35 degrees Celsius, and H is equal to, this is given in percent humidity. This is going to be a 5% humidity. And you could find what that maximum is, or what the max range is, by just plugging that in. That's going to be 28,900 minus 5 times 35 squared minus 6, 5, 35 minus 3, 5 squared plus 380, 35 plus 245. And that'll give you some value of a range in kilometers. That's the maximum range that we have with those optimal conditions, 35 degrees Celsius with 5% humidity.